Okay, my next two videos here are going to cover this section 1-3, more on functions and their graphs. The objectives for this section: identify when a function is increasing, decreasing, or constant. We want to find the intervals there. We'll just be looking at graphs. Use those graphs to locate the maximums and minimums, the peaks and the valleys. We'll figure out if a function is even, odd, or neither, and recognize symmetry. In this video, we'll do an example where we evaluate a piecewise function. In the next video, we'll start graphing and finish these objectives off. Piecewise functions and this difference quotient. That's a big setup for what's coming in calculus. So, here we got a graph, and this is just fuel efficiency in cars over the years. And on the y-axis, our average fuel efficiency, miles per gallon. Across the x-axis is the year of manufacture for these vehicles. And we can see here it says fuel efficiency decreased from 55 to 70. We see the graph is going down slightly. Here looks like the bottom of a valley. It says the minimum fuel efficiency was 14.1. That occurred back in 1970. And then as we continue to look on the graph, here's a steep line segment. The steepest segment there, fuel efficiency was increasing at the greatest rate, the fastest rate from the 70s to 80. And then here our graph is still going uphill. So we could say that fuel efficiency increased all the way from 1970 here at its low point, all the way up through 2009 where this data ends. Maximum fuel efficiency when this book was published, 32.6 miles per gallon. So there's some words in there that you're probably familiar with. Words like decreased, increased, minimum, maximum. In this section, we're going to enhance your intuitive understanding of ways of describing graphs by viewing these descriptions from the perspective of functions. For some definitions, of course, in math, all definitions have to be quite what they call rigorous, very well explained, leaving nothing that could be misconstrued. So here, if you read it, it's pretty confusing. A function is increasing on an open interval I if f of x sub 1 is less than f of x sub 2 whenever x1 is less than x2 for any x sub 1 and x sub 2 in the interval. Kind of confusing. But here, I'm going to get this their graph out of the way and just sort of make this from scratch, just how to attack these mathematical definitions. Here's an x and a y-axis. And let's start looking at some stuff in this definition. Here it says x1 is less than x2, or x sub 1 is less than x sub 2. When it comes to the x-axis, that means x sub 1 is going to be to the left of x sub 2. Yeah. 2. So x sub 1 is less than x sub 2. On the y-axis, where the outputs are, the y-axis or the f of x axis, f of x sub 1 is less than f of x sub 2. So that just tells me f of x sub 1 will be lower on the y-axis than f of x sub 2. So if I plot these points, here's x1 and it's f of x sub 1. That would be that point. x2 point that would be up here across from the f of x sub 2. If I connect those dots, that is increasing. If we read the graph left to right like we read the written language, that graph is increasing. So there we just sort of explained out that definition of increasing. And we could do a similar thing for decreasing. In the definition, they just changed the y-axis locations. Here would be x sub 1, now it's on top. X sub 2 is on the bottom. So now our point x sub 1 is high, our x sub 2 is low, and now that function would be decreasing. And if the graph is flat, all the x values or the y values are the same, we have a constant function. All right, example 1, the intervals on which the function increases, decreases, or constant. Let me make the graph a little bigger here. So we're going to find any intervals where the graph is increasing, where it is decreasing, or where it is constant. Oop. Get there. Constant. So I'm going to color code this. Here, this part sort of stands out to me. You know, we're in a valley down here, and we got a peak up here. So in between there, the graph is going uphill. So this red interval, what I colored red, is an increasing interval, and we want to take this to the x-axis. Here, we start, the left point here is at x is 0, and we're going to go until this point, x is 2. So our increasing interval occurs on the domain axis or the x-axis from 0 to 2. Now if I look at this part of the graph, if I go left to right, I'm going downhill, down, down, down. So this part is decreasing. Now we end our decreasing interval right here. So that's going to end at 0, but where did it begin? Now, don't get confused because this graph is going up real sharply, but as it goes up, it's also heading to the left. And way out here to the left on the x-axis is negative infinity. So there's a decreasing interval. And what about this piece here? We're at a peak, and after the peak, now it's downhill. So this peak started at 2. I'll just go up here, 2, comma. And again, we're heading down, but we're also heading to the right. As we head down toward negative infinity, we're heading toward the right toward positive infinity. So 2 comma infinity. There's our increasing domain, and there's where we decrease, and there's no spot on the graph that's constant, so I'll give it an NA, not applicable to this problem. All right, letter B here. Increase, decrease, constant. That's supposed to be a, so that looks like an E. It's supposed to be constant. So here we can see we are increasing, increase, going uphill. And that goes from x is 0 to, we're going to head way out this way, so that would be infinity. 0 to 2, we are increasing. Now, you know, there's an open circle there. If we were talking domain, we would want a parenthesis there, maybe a bracket on the other end. But here we're talking about intervals. And, you know, we're not talking about individual points on the end of intervals, so we're always going to use parentheses here. Well, let's see, is there any spot the graph is decreasing? Well, not that I can see. Maybe that's an NA, not applicable. And we do have a constant spot now. It sticks out like a sore thumb. It's the flat part of the graph, and it's flat from here all the way over to the left. So that would be negative infinity all the way to 0. Oh, and what am I doing? Increasing 0 to 2. No, it's 0 to infinity. I can't believe you didn't say anything about that. Okay, that's better. So we're increasing 0 to infinity, constant from negative infinity to 0. Up next, mins and maxes, relative mins and maxes. These are just the hills and the valleys on the graph. And the book says the point at which a function changes from increasing to decreasing or decreasing back to increasing, that behavior can be used to find the relative minimums and relative maximums of a function. So here's our confusing official mathematics definitions. 1, a function value f of a is a maximum of f if there exists an open interval containing point a such that f of a is greater than f of x for all x's not equal to a in that interval. So again, we're looking at a max. So here's our x and y axis. We have some output f of a. Here's a. Oops. Here would be its output f of a. And I'm going to just put that dot right here. There we go. And then it says that is a max if f of a is greater than all other f of x's. Well, here's f of a, so that means all the f of x's around it have to be down here. So I could, you know, put a few, well, this doesn't do dots very well. Put some points like down here. They're all going to definitely be below f of a. So if I connect them, that's got to be the peak. That's got to be a maximum. And then if you switch the inequality, that turns into a min. It means here we're at the bottom of a valley. All the other points around it are higher up on the y-axis. And sometimes it says here, you can see the word local instead of relative min or max. And you know what they mean by that. Here we got a few peaks. This is a relative max. It's higher than all the points around it. This is also a relative max or a local max. In its neighborhood, it's the highest point. Same thing here would be another relative or local max. I can't remember if it's somewhere else in this book. You definitely see it in calculus. This one up here would be called the global max as opposed to the local. This would be the highest of all the maxes. Now here it looks like there's a great question. Oh, and I sort of already talked about this. Do you use the x coordinates or the y coordinates to describe where functions increase, decrease, or constant? And the answer is the open intervals describing where functions increase, decrease, or constant use the x coordinates, not the y's. Furthermore, points are not used in these descriptions. Okay. Now, if the graph of a function is given, you can often visually locate the number or numbers at which the function has these mins and maxes. For example, I'll drag up this graph here in a minute and we'll figure out where these mins and maxes are. Let me put this down here and I'll bring the graph up here. Now this graph, we haven't covered it yet. This is actually a trig function graph. We'll be getting to these in a couple of chapters. But let's look here. We got this part of the graph and we're going down to a valley. So here is the bottom of that valley. That is going to be a relative minimum. And we can figure out the point. It says here, this one down here, f has a relative min at, well, f of what x value makes that minimum pop out of there. On the x-axis, that's negative pi over 2. Negative pi over 2. And the min, or that value is f of negative pi over 2 is its height on the y-axis, negative 1. So the point, we could write it as an ordered pair. Negative pi over 2 comma 1 is where the minimum is, the bottom of that valley. I'll switch over to blue ink here on the graph. Now we're up here and we're crossing this peak. So we have a peak here. That's our relative max. There we go. A relative max at, well, let's find the point. The x value that made it happen is here positive pi over 2. And our output value, that height is 1 on the y-axis. So we could say there's a max at pi over 2 comma 1. I'll switch back to red ink down here. This was our min. So there's our points, our mins, and our max. Again, we can get them just by looking at the graph sometimes. Next up, even and odd functions and symmetry. I'll leave that for you to read, blah, 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 blah. Here, the juicy stuff is in that definition box. Now here's a lot of notation, might be a little confusing. Function f is even if f of negative x is the exact same thing as f of x for all x values. I think about it like this. I'm going to do the even stuff in red. The most basic even function is just x squared. And just think about two easy points. Here's positive 2. If I square 2, the output value is 4. So there would be a point. What happens if we put negative 2 in there? Negative 2 quantity squared would also be positive 4. Get up there. Come on, there we go. So if we graph a parabola, there is our even function. And, here's our x values. We had 2 and negative 2. So f of negative x, or negative 2, was the exact same thing as f of 2. They both gave me the same output value of 4. So maybe that made that notation a little, make a little more sense there. F of negative x and f of x is the same thing. Here, our f of negative 2 is exactly equal to f of positive 2, and that value for both of them was 4. So that function is even, and this is coming up on a later slide. Let me move this up a bit. This has y-axis symmetry. So y-axis symmetry. Each point in quadrant 1 is reflected over into quadrant 2 around the y-axis. So it has that y-axis symmetry. Now I'll switch over to blue ink for an odd function. Now for odd, it says f of negative x is the exact same thing as negative f of x. Up here, it looked like the negative just disappeared. Like this f just ate that negative sign up and it's gone. In an odd function, it's like the negative sign escapes. Here it is inside the parenthesis with the f, or the x. It also escapes outside the parenthesis, and now it's out here in front of the f. It doesn't just disappear. So this, just think of a simple function, x cubed. If I put in positive 2, 2 cubed is 8. So that would give me this dot up here. If I put in negative 2, negative 2 to the third is negative 8. So remember, the x cubed graph looks sort of like this. Here, this might clear up the notation. F of negative x, there it is. F of negative x is the same thing as the negative of f of x. See, if I take out this f of x and replace it with this 8, that negative sign would hit it, and now it's the same thing as f of negative x. F of negative 2 is negative 8. There we go. And this is origin symmetry. Origin symmetric. We're symmetric about the origin. All right. So it says here every term on the right side of the equation of an odd function, blah, blah. Okay, there we go. So there's, in a nutshell, the difference between even and odd functions. Even functions are symmetric to the y-axis. Odd functions both start with the letter O, odd function, and origin symmetric. And this leads us to a little test if we want to figure out if a function is even or odd or neither. Now, I've been teaching my students to set it up like this. I'm going to start with the original function f of x. That is x cubed minus 6x. And this cube is going to bug me, so I'm going to throw that one in the garbage and hopefully make, there we go. Now, I'm going to come straight across here, and I'm going to do the negative of f of x. So it's like I put a negative out here. Now imagine there's parenthesis around this and distribute a negative. So that would be negative x cubed plus 6x. I just switched the signs. So here's f of x. Here is the negative of f of x. Now the test, we're going to evaluate f of negative x. If what we get here simplifies to our original equation, it is an even function. If what we simplify here perfectly matches our negation of f of x, it's an odd function. If it doesn't match either of those, it's neither even nor odd. So I'm going to take this x cubed minus 6x. It was x cubed minus 6x. Oops. There. I'm going to replace the x with a now negative x. So let's see what happens. Negative x to the third is a negative times a negative times a negative, which is negative x to the third. And then here, the minus times minus will turn into a plus 6x. So here's our simplified answer. Did it get us back to the original? No, so it's not even. Did it take us over here to this negation? Yeah, they match perfectly. So part A here, this function is odd. An odd function. Letter B. G of x is x to the fourth minus 2x squared. And then right across from it, I'm going to write its negation, negative g of x. So I'm going to switch both of these signs. Now it's a negative x to the fourth, and it's a plus 2x squared. Okay, coming down below, I'm going to do the test. We're going to put a negative through the original g function. So that was x to the fourth minus 2x squared. In those parentheses, now we put a negative x. Now with an even exponent, like here, the squared is going to be a negative times a negative. So this is going to turn into a positive. Same thing will happen with a fourth power. Any even power, this negative will square away. So this turns into x to the fourth. We still have this minus because this minus got squared away. So here is our g of negative x. Did that take us over here to the negation? No. So it's not an odd function. We got right back to where we originally started. So that means we're even. Our f of x, or in this case, our g of x, was the same as g of negative x. G of x and g of negative x are the same, so that is an even function. Letter C, our last one. So this is h of x is x squared plus 2x plus 1. I'm going to negate that negative h of x. So now the x squared term is minus, the 2x is minus, and the 1 is minus. And now we'll come down and find the h of negative x. So our first parenthesis was something squared, and then 2 times something and plus 1. In those parentheses is now a negative x. So here, the negative will square away. Negative and negative is positive, so that becomes a plus x squared. Here, the positive 2 and the times negative x will turn that into a minus 2x. And then we got a plus 1. Did that get us back to where we started? No, this sign is off, so it's not even. Did it take us over here to the negation? No, because we need a minus here and for the constant 1, so it didn't match that. It's not even, it's not odd, it's neither. Neither. Now let's see what even and odd functions tell us about the function's graph. Begin with x squared minus 4. We can see it here in the figure, parabola. The function is even because f of negative x is the same as f of x if we examine some of the pairs of points as shown. Like here, 3, 5 is this point, and then we have negative 3 with the same output 5. Notice the x values are positive and negative, y values are the same. Same thing here at negative 2, 0 and 2, 0. The x values are positives and negatives of the same number. The outputs are identical. Blah, 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 blah. This is what it means for a graph to be symmetric with respect to the y-axis. The graph is symmetric to the y-axis if for every point x comma y on the graph, negative x comma y is also on the graph. All even functions have this kind of symmetry. Again, it looks like if, oh yeah, I should be able to do this. If I just sort of color in this half of the graph with red ink, it's kind of like I can take that piece and flip it over the y-axis. And now it's going to land right on the other side. And I could always flip it back. Boom, boom. So there's our y-axis symmetry. The graph of an even function, f of negative x is the same as f of x, is symmetric with respect to the y-axis, like we just saw on that last slide. A graph is symmetric with respect to the origin if for any point on the graph x comma y, negative x comma negative y is also on the graph. Both signs changed. Observe that first and third quadrant portions of x cubed are reflections of one another with respect to the origin. So here is the xy. Oh, that's pretty terrible. Let's do this. Okay. Oop. So here in the first quadrant, x cubed looks like this, and in the third quadrant, it's coming down like this. Now, they said it's a reflection about the origin, which is true, or you could also look at it as it's a reflection across both axes. So here I could take this part and first reflects it over the y-axis, and then over the x-axis, and now it lands down on this other part. Or I could do it over in reverse order. I could do it over the x-axis first and be down here, and then flip it over the y-axis and land right back on top of it. So symmetric to the origin also is kind of like being symmetric to both axes at the same time. And before we talk about this, let me, I didn't mention this in class, I usually save this for the next day, but the so-called shortcut if a function is even or odd. If a function is even, it will have all even exponents, like x squared or x to the 6th plus x to the 4th plus x squared. So as long as all the exponents of our variables here are even, it's an even function. And we can also get away with adding or subtracting a constant, like x to the 4th plus or minus 10, because what that plus or minus does is shift us up or down. Here's x to the fourth. If I do x to the fourth plus 10, I move it up here. It's still symmetric to the y-axis. If it's a minus 10, I move it down here. It is still symmetric to the y-axis. So even functions can have a constant on the end, and it won't get messed up. Odd functions, on the other hand, must have odd exponents, like x cubed or x to the seventh plus x to the fifth minus x to the third. So it has to have all odd exponents, no constants allowed. You're not allowed to add or subtract a constant. And if we think about it this way, many odd functions do go through the origin. They don't have to. But if this is just my basic old x cubed graph, if I do x cubed plus 1, it's no longer going through the origin. It's no longer origin symmetric. Or if I'm here and I go down 1, I'm no longer origin symmetric. So shifting an odd function will throw off the symmetry. Shifting an even function up and down is fine. Last example here are these piecewise function. This example is a cell phone plan, and they're charging you $20 a month or $20 per month by 60 minutes. If you need more than 60 minutes, additional minutes are 40 cents each. So we can represent this plan mathematically by writing the total cost, capital C, as a function of a number of calling minutes t for time. So C of t. If your time is anywhere between 0 and 60, you made no calls or you made 60 minutes worth of calls, you're charged $20. If you are greater than 60, we now got to use this equation. Put the t in here, subtract 60, multiply that by 40 cents, and add 20 to it. And that will be the total cost. So this is a piecewise function. And it all comes down to here, which piece of the function do you use? If your t is between 0 and 60, put it in the top piece. Greater than 60, put it in the bottom piece. So a function that is defined by two or more equations over a specified domain is called a piecewise function. Many cell phone plans can be represented with piecewise functions. Here's a graph that describes the one we were just talking about. So from 0 to 60 minutes, you're down here paying a flat $20 rate. After 60 minutes, you start going up on this graph. More minutes mean more cost. So here in example 3, this is the same one from the graph there. Find and interpret each of the following. So C of 30. So if I go to the piecewise function up here, 30 is somewhere in here. And if we had a t over here, we'd plug in that number for it, but there's nothing. Our answer is just 20. C of 30 is equal to 20. 20. So that just says to interpret that, we used 30 minutes of our cell phone plan. We're still paying $20. Even if we only did 10 minutes of calls, we'd still be paying $20. 60 minutes of calls, still $20. Now part B, C of 100, is a little different. 100 is outside this range. We're not between 0 and 60. Now we're here. So our t value is 100. That's going to go in right there. So C of 100 is going to be 20 plus 0.4 quantity t minus 60. And these computations are pretty straightforward. If we put 100 in here, 100 minus 60 is 40. 40 times 0.4 is 16. 20 plus 16 is $36. Let's put a dollar sign on there. We're talking money. So the interpretation of it is, well, we've used more than 60 minutes. We've gone above the flat rate of $20. So since we made an extra 40 minutes of calls, our bill is now up to $36. And there we go. That's example 3. Now some practice problems for you. You know the drill. Pause the video, then try out the problems. Fire the video back up and see if you got it right. Ooh, and I shouldn't have showed you the shortcut on even and odd until after those questions. All right, checkpoint 1. Let's see here. I look at the graph and I pick out the odd thing. Like here we are decreasing a little bit in the middle. So I would start here by going after the decreasing part of this graph. Where's the graph decreasing? It looks like here we got a hill at -1 and we got a valley at +1 and oops, lost my ink. There we go. So from -1 to 1, we're decreasing. increasing. Here we are, this we left off at 1 here, so 1, and now the graph goes up, 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 up. It's increasing, so we're increasing from 1 to infinity. Here, our graph is also increasing. We're going up, 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 up until we hit the negative 1. So that will end the interval. And remember, as we're heading down here to negative infinity on the y-axis, we're also heading to the left to negative infinity on the x-axis. And that covers everything on the number line. Negative infinity, negative 1, negative 1 to 1, and then 1 off to infinity. Okay. Now here, I guess I did spill the beans on the shortcut, so we can just do that. On the homework, on the worksheet, the last two problems, it's not as obvious as what's going on here. Even I just had to sit them down and compute it the way I showed you how to do it in the example. But here, x squared is even. The constant moving up or down doesn't mess anything up. So a is even. Here is 7x cubed minus x to the first. Every exponent is odd, so we're good to go. That's an odd function. Here we have an odd exponent, x to the fifth. But a constant is going to throw that symmetry off the origin. So here is a neither. Not even, not odd, neither. And finally, this goes right back to the, let me just drop this right on the graph here. Here we are. Oop, get out of there. There we get. Come on. There we go. There it is. So use the function in example 3 to find and interpret each of these. So C of 40. 40 is in between 0 and 60. Right here is 40. If we look up, we're still on the flat part of the graph. So C of 40 is 20. We're still paying the flat rate of up to 60 minutes. So there we didn't even use all of our allotted minutes. C of 80, though, is a little different. Here's 80. Now we're going uphill on that. So that little formula right here is 20 plus 0.4 times t minus 60. RT is 80. 80 minus 60 is 20. 0.4 times 20 is 8. So that becomes 20 plus 8, or 28 bucks. The flat rate was 20, and we did a few minutes over our 60 minutes, so we're paying a few more dollars for that phone call. And I think that's it. Yeah, we're good on that. Just real quick. Even, odd, or neither. X cubed minus x, odd exponent. So that's, was that the same one from the huddle? And your x squared minus x. X squared, x to the first. We got an even and an odd, so that would also be neither. And a worksheet for homework.